Start show? अच्छा जी, बिस्मिल्लाहिर्रहमानिर्रहीम. We are starting now the next chapter, consolidation. अच्छा जी. In the first chapter, what we discussed was effective stress concept, right? And then what is what is consolidation process? That is what we discuss. Now, in this chapter, the whole chapter is dedicated to the topic of consolidation, right? It is very important topic, and it will take around 5 lectures to complete this chapter. 5 classes to complete this chapter. Oda bos na ko mode ke raji. जी अवल मोड तो भराशी एनिमेशन मोड या न लगाया ना ठीक है चले ठीक है अच्छा जी in this chapter these are the topics that we would discuss. What is one dimensional consolidation? Odometer test give you is a test that you would conduct in the laboratory, and this test would give you the parameters required for consolidation determination. Then we would discuss E sigma curve and E log sigma curve. Then we would discuss what is over-consolidation ratio, over-consolidated clay, and normally consolidated clay. Then we would discuss compression index and recompression index indices, determination of pre-consolidation pressure by Casagrande method, and some field correction to this curve, coefficient of volume compressibility, consolidation settlement calculation for NCC and OCC clay. These are the topics that deal with the first part of this chapter. And then we have a second part of this chapter. Both we would discuss. अच्छा जी. You see, this is a building, right? This is a building. It is, and below this building, there is saturated clay or silt, right? When the building load is imposed on the soil layer, there is compression of this soil, right? If you take a small element within the body of this consolidating layer, we will see that this element is compressed by amount delta H. Delta H is the settlement. If the area of the loaded area is greater than the thickness of the layer, then this element would only compress in the vertical direction, right? And the compression or strain in the horizontal or lateral direction is assumed to be zero. So we call this one-dimensional consolidation, right? So due to the building load, the soil element would get compressed. All the soil element in the layer would get compressed, and at the foundation level, there will be a settlement which is called delta HC. Now, we are interested to find out, and you know that consolidation occurs in soil of low permeability like silt and clays, right? So we are interested to find out what is the value of delta HC, how much the building would settle. This is what we are interested in. In order to find out this value, what we do, we take a soil specimen from the body of the soil consolidating layer. How we will take? We will do a borehole, drill a borehole, and take an undisturbed soil specimen, right? And we then transport this undisturbed specimen transport transport to the laboratory. And in the laboratory we conduct test, right? We subject the soil specimen to the same stress ranges as in the site and find out how much this uh, soil specimen would compress. This test in the laboratory is called consolidation test or odometer test, that we would discuss shortly. After you conduct this test, we process the data and we find out consolidation parameters, which is CC, CR, MV, small cv, is not there, sigma p prime. These parameters then we use in the consolidation equation. There are certain equations that I would be discussing with you, and these equations would give us delta C, which is the foundation settlement. Any question? Do you have any question? Ji, any question you have? Muhammad Riyaz, are you there? Muhammad Riyaz Khan? Muhammad Riyaz, can you hear me?
सर आवाज आ रही है?
आपको आवाज आ रही है, गुड. Any question you can ask, otherwise we would move forward to next slide. Yes, slide.
ठीक है सर.
So you see, this is a graph. In the x-axis we have time in years. On the negative y-axis we have foundation settlement of the building, right? So what we see here, you see the settlement increases with time, and then it reaches almost asymptotically, right? It stops. So this last amount is the final consolidation settlement. This is the final consolidation settlement. Engineer is usually interested to find out this final foundation consolidation settlement, right? Because this is the one that he would consider in the foundation design of his structure. But if the permeability of the soil is very low, it will take a long time, maybe some centuries, to reach to this final settlement. And the design life of your structure would be maybe 50 years or 100 years. So you don't need to design your foundation for a settlement that would occur after centuries. So it is also important to know the rate of consolidation, when this settlement would occur, right? So this is called rate of consolidation. So in this chapter, we would draw this curve. This is the ultimate goal of this chapter, to draw this curve, which would give you final settlement, consolidation settlement, as well as the rate of consolidation. So the first part of this chapter would deal with the would deal with the final settlement. First part, we would find what is the final consolidation settlement. And the second part is related, second part of this chapter, which would be after a few classes, deals with the rate of consolidation. So this chapter, we have divided into two. Number one, how to find final consolidation settlement. In this part, we will not discuss when, how long it would take to reach to this final settlement. We would have no idea when this would occur. But the second part second part of this chapter would address this question: how long a particular settlement would take to occur, right? Do you have any question? So let's discuss the consolidation test, right? Let's discuss the consolidation test. This is consolidation test. This is consolidation apparatus you see in picture A, and this is schematics, a cross section of it. You see, this is soil specimen. This disc shape is soil specimen. Here in picture C, you see the soil specimen. This is the soil, undisturbed soil specimen. On top, and here it is. On top and bottom of this specimen, we keep filter paper. We put filter paper, and then on top and bottom of it, we take porous stone. So this soil specimen is sandwiched between two porous stones, one up and one below. This is porous stone. This is porous stone. Here in this picture, you can see the porous stone. Here are they. You see in picture B, near the filter paper, white filter paper, we have two porous stones. On the porous stone, we put the loading cap. This is loading cap, you see. This is loading cap, and then load. Another picture you can see, this is a soil specimen. The soil specimen is surrounded by a rigid ring, right? And then porous stone up and below, and then in picture G, you see the loading cap, and then you apply loads. The purpose of this ring, can anybody say what is the purpose of this rigid ring?
सर इसमें lateral deflection ना होने के लिए.
Yes, so that the consolidation or any compression occurs just in the vertical direction. Achha. What is the purpose of sandwiching this specimen in porous stones, up and below? Gee, what is the purpose of these porous stones?
सीपेट के लिए सर.
Any other body? सीपेज नहीं, ड्रेनेज के लिए. किस लिए? For the drainage.
Drainage.
Yes, because when the load is applied on this soil specimen, there will be excess pore water pressure develop into the soil specimen, and this, to dissipate this excess pore water pressure, the drainage should take place. And the drainage requires some free draining boundaries. If you don't provide porous stone, rather solid plates, then the water would not escape out of the saturated soil specimen and there won't be any compression, right? For the compression to take place, you need porous stones, free draining boundaries, right? So you keep all this setup in a pot which is filled with water, right? So the drainage occurs against this water, against the water. It is to simulate the water table at the site, right? The pressure, the water pressure, the pore water pressure in this soil station is much higher because of the load compared to the water pressure outside, right? So the drainage would occur, and the drainage would occur only in the vertical direction, right? And vertical direction. Some water would go up and some water drops would come down. You could use, instead of 2 porous stone, only 1 porous stone, and the test could be conducted, but it would take much more time because the drainage path now is longer. So to reduce the drainage path into half, you use porous stones, 2 porous stones, one above and one below. Do you have any question? Okay. So what you do, you apply, this is stress, this is compression, and this compression or settlement, compression, okay, compression or expansion and void ratio. Table that's the good 24 or 48 also. Okay, here you go. So what you do, you see, you apply some stress on the top of the soil specimen. The effect of this stress would be to generate excess pore water pressure into the soil specimen, right? This excess pore water pressure, because there are drainage boundaries available on top and bottom of the soil specimen, drainage would take place in the vertical direction, both above and below. As the water goes out of the soil specimen, it would be accompanied by corresponding compression of the soil specimen, right? The compression of the soil specimen would start, right? And after 24 hours, it would be complete. It would almost no more get compressed. At that state, the applied stress, which is the total stress, would be equal to the effective stress in the soil specimen, right? So when time is 0, applied stress is 0, delta H is 0, there would be no compression because it's just start, no load is applied, and the void ratio would be equal to E naught, which is the initial void ratio. Then you apply sigma 1 stress and keep this load for 24 hours. After 24 hours, when drainage is complete, sigma 1 prime would be equal to sigma 1, and the compression would increase from 0 to delta H1, and the void ratio would decrease from E0 to E1. Void ratio of the specimen would also change. Then you increase the load to sigma 2 and keep this sigma 2 for 24 hours. After 24 hours, the drainage would complete. There will be no excess pore water pressure in the soil specimen. Sigma 2 prime would be equal to sigma 2. And the compression would further increase to delta H2. The void ratio would be E2. It would further decrease. Similarly, you increase the stresses and you record the data for a week, for example, and you do some loading and then you do some unloading. When you unload the soil specimen, there will be a swell. Delta H would decrease and the void ratio would slightly increase, right? So what now we are going to do, we are going to plot stress versus void ratio curve. And let's see how it would look like. It would look like this. On the x-axis you have effective stress, on the y-axis you have void ratio. And you see, as you increase the effective stress, the void ratio decreases. At this point, you decrease the effective stress, the load on the soil specimen, so there would be a swelling or rebound or expansion, right? This is expansion because void ratio is increasing. When the void ratio is increasing, it means it is swelling. And then you reload the soil specimen, and again the void ratio decreases, and as you are increasing the effective stress. When the effective stress reaches to the previous point, again the curve follow the same path. It would follow this path. You know what I mean? Okay. This is expansion curve. This curve is called expansion curve because it is expanding. The soil is expanding, the soil is swelling. And this curve is called recompression curve because you are recompressing the soil specimen, right? The stress, you took the specimen to a particular stress level and then you decrease it, and then you are again taking the soil specimen to the same stress level, so you are recompressing the soil specimen. This curve is called recompression curve. Design mode this is called recompression curve. No, sorry, this is called expansion curve. Expansion curve. And this curve is called recompression curve. Because you are recompressing the soil specimen. Now, in the next slide, what we are going to do, we are going to plot the same data on a log x-axis. So we would plot the same data on log, sigma prime, and E. And let's see how the shape would be. So the shape is here. This should come. You see, the same data when plotted, you have a curved path, then a straight line, then an expansion curve, and then recompression curve, and but by the time it reaches to the same stress level, it becomes linear, right? So important thing here to note is this, that the curve is, the recompression curve is not a straight line, rather a curve, and when it reaches to the same stress level, it becomes linear, right? So whenever you are recompressing a soil specimen to the same stress level, it would behave, its behavior would be in form of a curve, not a straight line. But once it reaches to a highest stress level, right, it would be a straight line. Because this in straight line here, this has not been subject to a maximum pressure. This is the maximum pressure, right? So it is a linear line. That's why we call this as a virgin compression. Virgin compression. Why we call this a virgin compression? Because the soil at this point is subject to the maximum pressure, right? That is greater than any past pressure. But when you are at this point in the recompression zone, when you are in the recompression zone, the stress is here, for example, this is stress, is smaller than this stress, which was its past stress, right? So when the present stress is less than the past stress, it would be on the recompression curve. But once the stress is more than the past stress, like this is greater than the past stress, it is linear. So you got the idea? If you have any question, you can ask.
Sir?
Ji. If you have any question, you can ask.
सर इसका पर्पस क्या है ई वर्सेस लॉग इसका पर्पस क्या है ई वर्सेस लॉग सिग्मा डैश इस कर्व का
पर्पस क्या है? पर्पस आपको मैं बताता हूँ ना, पहले इस ग्राफ को समझें, ठीक है ना? पर्पस तो मैंने आपको बिल्कुल लेक्चर के स्टार्ट में बता दिया कि हमारा बिल्डिंग सेटल हो रहा है, ठीक है? वो सेटलमेंट मालूम करने के लिए हमने एक सॉइल स्पेसिमेन लिया, कंसोलिडेशन टेस्ट किया, उससे हम पैरामीटर निकालेंगे, टेस्ट से पैरामीटर्स वो इक्वेशन में डालेंगे, इक्वेशन से फिर हमारे पास सेटलमेंट आ जाएगी। ये तो बिल्कुल चैप्टर के स्टार्ट में मैंने ये एक्सप्लेन किया आपको कि इसका क्या पर्पस है। लॉग स्केल, इससे पहले हमने लॉग इस्तेमाल नहीं किया और अब हमने लॉग स्केल पे इसलिए प्लॉट किया कि इसमें आपको काफी चीजें अभी और भी सामने आ जाएंगी। देखें, इसमें वो सारा कर्व था, मगर लॉग की वजह से इसमें लीनियर पार्ट भी आ गया और कर्व पार्ट भी आ गया, और हर एक की अपनी एक खसूसियत है। एवरी पार्ट हैज इट्स ओन प्रॉपर्टीज एंड सिग्निफिकेंस, because the curved part is a recompression, which signifies that in the past the past stress is maximum than the present stress. And when you have a linear behavior, it means that here the current state of stress is the maximum one. Ji, any question? So my question is now that this part is curve and this is then linear. The first part is a curve part, right? And this is linear part, right? So why is this? Why this is curve? This is a curve part and this is linear part. G, if you understood this curve, then answer me why this is curve and this is linear. G. No, no es tampoco. Alam mobile के वाला खाना तिल बना खाना चलता हाँ आवाज में लगा पे बंद जी कोई आंसर दे गलत दे दे if you have any idea if you are hearing my voice
सर पहले जब सेटलमेंट शुरू होती है तो उसमें थोड़ी सी स्ट्रेस के साथ वो सेटलमेंट ज़्यादा होती है, फिर एक खास टाइम के बाद वो फिर कांस्टेंट हो जाती है, मतलब जितना स्ट्रेस ज़्यादा होता है तो उतनी सेटलमेंट होती है।
नहीं, my question is this, why this is a recompression, right? This curve, this is a recompression curve, right? I have told you that whenever there is a curve part, it signifies recompression. Recompression means in the past, the stress is more than the present one. Here, the stress level is less than the previous one, the past. It occurs, for example, when you take a soil specimen from a site where there was, for example, some fill material placed some 100 years ago or 50 years ago, and that fill material has imposed some stresses in the ground. But afterward, that fill was removed, right? Now, the current state of stress in the soil specimen in the soil is less than the past one. If you take that soil specimen and bring it to the lab, right, and you start the test, and you apply stresses, and these stresses are less than the ones that was 100 years ago imposed by the fill material. So you will have a curve portion, right? But by the time that stress level, that maximum stress level is exceeded, it will linear out. You will have a virgin compression curve. Now you understood? Hello?
यस सर समझ आ गया।
अच्छा
जी सर।
Okay. So let's on the basis of this curve, let's define few terms over. Okay. This pass pressure is called pre-consolidation pressure. This pass pressure is called pre-consolidation pressure. That I told you that there is a fill material, for example, previously on the ground, which has imposed some stresses, right? Now in the lab you are increasing the stress, but by the time you reach that maximum stress in the past, it will be linear. So that maximum pressure in the past is called the pre-consolidation pressure. ठीक है ना? So it would be somewhere here between the linear part and the compression part. This is called the pre-consolidation pressure. And this is the beauty of the clay and the silt material, that it keeps its stress history. It remembers stress history. Maybe 1,000 years ago or 100 years ago or even few days ago, if there was a fill material or some glacier deposit or some building on the ground and it is no longer there, so it remembers that maximum pressure in the past. And when you bring it to the lab and you start increasing the stress, it will be recompression. But by the time it reaches to that maximum pressure in the past, it will become linear. So this maximum pressure in the past is called the pre-consolidation pressure, right? So on the basis of this, we do some definition. What is an over-consolidation ratio? So it is the ratio of the maximum stress in the past divided by the current pressure. We divide by the current effective stress. For example, this is soil, and this is a soil specimen, right? And there was some stress in the past because of a fill material, right? So that will be sigma p prime. Sigma p prime. But once this stress is removed, this fill is removed, the same soil specimen would be subject to current state of stress, which is sigma naught prime, right? So sigma naught prime, this sigma naught prime, this sigma naught prime is less than sigma p prime, which was in the past. So the ratio is called over-consolidation ratio. What is an over-consolidated clay? If this past pressure is greater than the current pressure, so the over-consolidation ratio would be greater than 1. So if this is greater than 1, this soil is called over-consolidated clay. But if there was no fill on the soil, there was no fill in the soil, right? And the present pressure is equal to the maximum pressure, right? So so sigma p would be equal to sigma naught, and over-consolidation ratio would be equal to 1. So such soil are called normally consolidated clay. Based upon the OCR, we classify the soil like, if OCR is 1, the soil is called normally consolidated clay. If OCR is between 1 and 2, it's called slightly over-consolidated clay. If it is between 2 and 8, it is called over-consolidated soil. But if it is greater than 8, it is called highly over-consolidated soils. So the best soils for foundation are those which are over-consolidated. And if you are constructing your foundation on normally consolidated clays, so you have to be careful. There would be large settlements, right? If you have any question, you can ask. Otherwise, we would move forward.
Excuse me, sir.
So we talk about pre-consolidation pressure. How you will find the pre-consolidation stress from the curve. The simple method is to see when there is a break between this curved part and the straight part, that corresponds to the pre-concentration pressure. Once the stress is more than the pre-concentration pressure, the curve would be linear, right? So you search for that break in the curve, and that is approximately the pre-concentration pressure. But the method, which is a bit more exact than this visual method, is proposed by Casagrande method. Casagrande. How to find the pre-concentration pressure? It is a construction method, graphical construction method, right? To find this maximum pressure, effective stress that has acted upon the soil. What you do? You obtain this curve. You obtain this curve from the laboratory, from the odometer test, right? From the consolidation test, which you will conducted in your laboratory, in the lab work. So you get this curve. What you do, you locate a point of maximum curvature on the curve part just by visually seeing which part will have the maximum curvature on the curve part. You just locate it and call it point D. Then you draw a horizontal line on this D, point D. Then you draw a tangent on the point D. Then you draw a bisector. The angle between the horizontal line and the tangent line, this is the angle, right? So you bisect this angle. This and this angle is equal, right? This is theta and this is theta. These are equal. So this is a bisector of the angle, of this whole angle. What then you do, you have a linear part, right? So you produce this linear part back, like this. You see, I have produced this back. This point of intersection between the produced back line and the bisector, you locate this point here. That point is very important. That point corresponds to pre-consolidation pressure. So this is how you find out the pre-consolidation pressure. Lal Zaman, are you there?
Yes, sir. Yes, sir.
Okay. Do you have any question?
No, sir.
Okay. Sayyid Wajahat Ali Shah.
Yes, sir. Yes, sir.
Do you have any question?
No, sir. Sir, समझ आ रही?
Sayyid Wajahat, are you repeating this?
Yes, sir. Sir, I want to improve my grade.
Okay, and understanding.
Yes, sir.
Okay. Acha. So if you have any question, Sayyid Wajahat, you can ask.
Okay, sir.
So this is how you find the pre-consolidation pressure. So that's the beauty. You don't know, you have taken a soil specimen from the site, but you do not know whether in the past was there any more stress than the present one, or was there not, right? By doing this type of construction, you find the pre-consolidation pressure. So Wajahat Ali Shah, can you Tell me, is this a normally consolidated clay or is this an over consolidated clay?
Sir, which one clays? Sir, sir, this is pre-consolidation we have found out.
So which type of soil is this? How you would know, is this soil is normally consolidated or is this an over consolidated?
Sir, from the OCR we will check it.
Check it. Check it right
Yes.
now. How you would check it? Anyone can answer?
सर प्री कंसोलिडेशन प्रेशर कम है उससे तो
किससे?
नो क्योंकि पहले इस पर इतना स्ट्रेस नहीं आया था, अभी आ गया है तो इसलिए नीचे चला गया, तो मेरे ख्याल से नॉर्मल है।
शाहजेब आप बताएं। शाहजेब आप मौजूद हैं कि नहीं? शाहजेब मेरे ख्याल में लॉग इन होके सो गया है। सीआर शाहजेब को बता दो फिर। अच्छा जी, मैं एक्सप्लेन करता हूँ। वजाहत अली शाह।
ओके सर।
मैं एक्सप्लेन करता हूँ। देखें,
ओके सर।
ये आपके पास साइट है, फील्ड में गए आपने, इस डेप्थ से आपने सॉइल स्पेसिमेन को लिया है, ठीक है ना। इस डेप्थ का यहाँ पे आप इफेक्टिव स्ट्रेस मालूम करें, वो सिग्मा नॉट प्राइम मालूम करें। सिग्मा नॉट प्राइम, और ये किसके बराबर होगा? सिग्मा नॉट प्राइम। कैन एनीबॉडी से?
सर डेप्थ और यूनिट वेट।
इफेक्टिव यूनिट वेट। क्या?
इफेक्टिव यूनिट वेट।
The first chapter deals with this calculation, right? You know this stress, right? Now you took this sample and brought it to the laboratory, right? And you did this construction. If this sigma p prime, if the sigma naught prime is somewhere here, oh my gosh. अब वर्ष रिमूव की तरह। अच्छा, अच्छा जी, if this sigma naught prime which you have calculated is coming somewhere here, so which type of soil is this? जी वजाहत?
ओवर कंसिडरेटेड सर।
Over considered because sigma p prime is greater than sigma naught prime and OCR would be greater than 1. But if this sigma naught prime comes out to be exactly equal to or close, very close to sigma p prime, that soil is
नॉर्मल कंसिडरेटेड।
normally considered clay. अच्छा जी, okay. Now you got the idea. You learned at least 4 things on this slide. Number 1 is the pre-consolidation pressure, how to find it using Casagrande method. Second thing that you learned, how to find sigma naught prime, and then how you would decide if this is a normally consolidated clay or an over consolidated clay, and one thing that when it would be curved and when it will be a straight line. So when the stress is more than sigma p prime, you see here, if you reach here, you see that's linear because this stress is greater than the sigma p prime. As long as the sigma naught prime is less than sigma p prime, you will have, if the applied stress is less than the sigma p prime, you will have curved part, and then you will be having a linear part. When you reverse it again, you see now this is the maximum stress, and now this stress is less than this stress, so you have a curved part. And when reaches the maximum one, it again linears out. You understood what I mean? Wajahat?
Yes, sir. Yes, sir.
Now you have any idea? If you have any question, you can ask.
Yes, sir. समझ आ गया, sir.
Muhammad Usama? Muhammad Usama?
Yes, sir.
अच्छा जी, आगे जाते हैं. अच्छा जी, अब हमने ये what we did, we conducted this test on undisturbed soil specimen. Undisturbed soil specimen are those specimens which we collect from the site very carefully so that its moisture content, unit weight, and natural fabrics don't get disturbed, right? But no matter how much careful you are, there will be some disturbance, right? And the behavior of the curve you obtain from the lab and the actual behavior in the field would be slightly different. So we need to carry out some corrections on the curve so that it represents and come close to the field condition. For this, we do separate correction for normally consolidated clay and separate correction for over consolidated clay, right? So let's start first the field correction for the normally consolidated clay. In situ E log sigma. In situ means field curve for NCC. नॉर्मली कंसिडर्ड क्ले के लिए आप कैसे करेक्शन करेंगे? सो you know what I mean? अच्छा जी, so what you do, you have this curve. This is the curve that you obtained from the lab. First of all, what you do, you find the pre-consolidation pressure using Casagrande method, which you have just done. And then you found the sigma naught prime, and both are equal, so that is in a normally consolidated clay. ठीक है ना? अब how to correct this curve? You find E naught, which is the void ratio, initial void ratio of the soil specimen, and you use the well-known equation, which is GS, which is the specific gravity of soil, moisture content of the soil, right, divided by degree of saturation S. That will give you E naught. And degree of saturation, if it is assumed to be 100%, so the E would be just GS, specific gravity of the soil solids, into natural moisture content, Wn. S would be N, equal to 1. So no need here. We would do an example where you will know it. So E naught you located here. Draw a horizontal line, and where it cancels the vertical line, this is control point number 1. You mark this point. That point you would need. This point is of significance. Next, you locate 0.42 E naught. You multiply E naught with 0.42 and you locate it somewhere here, where it comes, right? Then draw a horizontal line, and where it cancels this straight line, virgin curve, you mark it as 2. Now you join point 1 with point 2. Point 1 with point 2. So now the virgin curve, which was this straight line, you have replaced this with this line. Now this is the virgin curve, corrected virgin curve. This is called field virgin compression curve. This is called corrected curve. And this is laboratory virgin compression curve, right? This is field. So you use this in calculation, this curve, this. The slope of this curve is called CC, or compression index, right? So this is how you corrected the normally consolidated clay. You have any question, you can ask. We can simply represent the whole curve by using this. You see, only this information. This is corrected or field virgin compression curve. The slope is CC. This is sigma naught prime, sigma p prime. This corresponds with G naught. This was a 0.1, right? And this was 0.2. Okay? Sigma naught prime is equal to plus delta sigma. Here E naught, right? As you increase the stress from sigma naught prime to delta sigma, the void ratio would decrease from E naught to E1. Okay? Now let's correct this correction for the normally consolidated clay. Now let's do the same kind of correction for an over consolidated clay. In situ E log sigma curve for over consolidated clay. Again, the famous curve, the infamous curve now. You see, there are more loops here. So this is an over consolidated clay. Yet you do not know if this is normally consolidated clay or an over consolidated clay. Now you would know if it is normally consolidated or an over consolidated clay. First, you carry out the Casagrande correction, Casagrande construction method to find sigma p prime. Here you go. This is sigma p prime. Then you find the field current effective vertical stress. It is this. Since sigma p prime is greater than sigma naught prime, it means that this is an over consolidated clay. The rest of the procedure is not much different than what we studied. You locate the point of E naught, which is initial void ratio, and draw a horizontal line, and where it cuts, intersects the sigma naught prime, that is control point number 1 for you. Then you draw a slope between a mean slope between the swell curve and the recompression curve. This is the line, and take this line up to join 1. Here, this line now is parallel to this. That is point number 2. Now, the rest of the procedure is exactly same. You locate point 42 E naught, draw a horizontal line where it intersects the straight line. You call this point 3. Now you join 2 with 3. So you have corrected, carry out the needed correction, right? So here you go. This is field virgin compression 1 in CC, the same like a normal concentrated. One thing which is additional is the CR, recompression index, the slope of the recompression curve. The slope, this is also CR. The slope is also CR here because this is recompression. This is CR, right? And this is CC. Simplified way you can show it here. This is CR, right? This is CC, right? This is sigma naught prime corresponds to E naught. सिर्फ CR होता बस दान 1 2 दाओ R सौगा कहीं sigma naught CR and this is CC. So you have CC, slope of the virgin curve, which is called CC is the compression index. You have CR, slope of the recompression index, right? You have sigma naught prime, current effective stress that corresponds to the initial void ratio, and you have sigma P prime. If you have any question, you can ask. Amna Khan. Miss Amna Khan, are you there?
Yes, sir. Clear, sir.
Clear है?
जी.
समझ आ गई है?
जी, sir.
अच्छा. Let's move on and find how you will calculate CC, which is the slope of the normally concentrated clay, slope of the recompression. Slope of the compression index CC. आपको पता है ये slope हमने मालूम करना है. This is the slope of the CC. This is a normally concentrated clay. Sigma naught prime equal to sigma P prime. This is a virgin curve. This is slope CC, right? We want to find this CC. So this is sigma naught prime and this is an additional set delta sigma. So at this point 2, we have the stress sigma naught prime plus delta sigma. Sigma naught prime plus delta sigma. आपको पता है the slope is equal to delta y over delta x. Delta y over delta x. So delta y is this. And you see it is E naught minus E1 is delta y. And delta x is this. This stress minus this stress. But log, because it's a log scale, so that would be equal to log sigma naught prime plus delta sigma minus sigma naught prime. So delta y is E naught minus E1 and delta x is log sigma naught prime plus delta sigma minus log sigma naught prime. So you put this into this equation. You put these in this equation. You will get CC is equal to this. But you know that log with a minus sign would be come in division. Log sigma naught prime plus delta sigma over sigma naught prime. So this is the equation. This is the equation of CC. This is how from the graph you will find the value of CC. So the points are not important whether you take this point or this point or this point. any 2 points on their curve will give you the same answer, right? As long as your both points lie on the straight line, from this equation, you will get this more or less the same answer. Now, let's find the slope of the recompression curve, which is CR. Recompression index CR is the slope of the recompression curve. So, the equation of the CC and CR are same, right? Only difference is you select 2 points on the recompression curve. Instead of on the compression curve, you select the 2 points on the recompression curve and use the same equation. But now E naught and E1 and sigma naught and delta sigma correspond to the stresses and void ratios selected on the recompression curve. You have any question? Ghulam Qadir Khan?
No, sir, clear.
Come on, Muhammad Osama is there or still just log in? Muhammad Osama?
Yes, sir.
Okay, are you there?
Yes, sir.
Okay, good. Acha ji. Let's move on to next parameter, consolidation parameter. So what we are doing, inconsistent with what I presented on the first slide, that we would conduct the consolidation test and then we process the graphs to find some parameters. So what we are doing on the same line. The value of CC, if it is less than 0.2, that is very low, soil of very low compressibility. If you have soil of very low compressibility, the CC would be about 0.2 or less than 0.2. But if CC is greater than 3.2, so that is extremely high, soil of extremely high compressibility. I suspect you cannot build any foundation on such type of soils. That's very difficult. That is organic type of soils. But if you have most soil lie in this range, 0.2 to 0.8. 0.2 to 0.4 is soil of low compressibility and 0.4 to 0.8 of medium compressibility. Good news is this, the soil in Peshawar lies in the very low compressibility. Its CC is about 0.2. The ratio of the CC or CR is 0.1 to 0.2. It means that 10 times to 20 times less than, right? 10 times less than, about 10 times to 5 times less than the CC value. Now you see that as the value of CC is more, the soil is more compressible. It is because as the value of CC is more, the slope, the inclination of the curve would be a lot more. The slope would be a lot more. As the slope is more, right, the settlement would be a lot more. And you see that CR, which is the recompression curve, its slope is 0.1 to 0.2 of CC. It means that recompression slope is very mild. CC is very steep and CR, the recompression index slope, recompression slope is very mild. It means that if your foundation stress is such that you are in the recompression part, is going to settle very less. but by the time it is more than the pre-consolidation pressure and you come into the normally consolidated part of the curve, there will be huge settlement. Now I'm going to derive a small equation. This is a phase diagram. This is soil solids. These are soil solids. And this part is void ratio, voids, which is fill of water in case of saturated soil, and we are discussing saturated soil. These are voids. These are fill of water. So we have Vs volume of solids or Hs height of soil solids. If we keep the area same, right? If you assume a unit area, so volume of the solids is equal to height of the solids. Similarly, here is the height of the voids or volume of the voids. When you apply load, there will be, what would happen? A drainage would occur, right? And as the water goes out, in corresponding settlement or compression would occur, which is delta H, right? We know that void ratio is equal to VV over VS or HV over SH. But if we assume HS is equal to 1, if we assume HS is equal to 1, E naught would be equal to HV. You see, here if you assume HS is equal to 1, HV will be equal to E naught, initial void ratio. So we can represent the same diagram in terms of void ratio. How? This is HV is equal to E naught as we proved, and HS we assume 1. So the total height would be equal to 1 plus E naught, 1 plus E naught. And that is the change in the void ratio, which corresponds to delta H. Now, from the ratios, delta H over H naught would be equal to delta E over E naught. Why? Here you see delta H is equal to, corresponds to this, and H naught corresponds to this. From this equation, we have delta H over H naught is equal to E naught minus E1 over 1 plus E naught. You got the idea? This is a small equation that we have proved, but it's very significant. It has large significance. Very simple equation to prove. Ji. Sajjad Khan.
Sir?
Ji.
Sir, why we take HS equals to 1? Why not HV equals to 1?
Because our purpose is solved when we take HS is equal to 1. अगर आप HV को लें तो E will be 1 over HS, तो वो तो बड़ा difficult हो जाएगा. Understand?
Yes, sir.
अब ठीक है ना, ये तो रेशोज हैं, ठीक है ना, रेशोज हैं, इसलिए इस तरह लिया गया है ताकि आसानी हो, वाइड रेशियो और हाइट्स को हम कंपेयर कर सकें, ठीक है ना. अब 100 भी ले सकती हैं, H is equal to 100, नो प्रॉब्लम, अकॉर्डिंगली द थिंग्स वुड चेंज. आप समझ गए?
यस सर.
आसानी के लिए 1 लिया गया, वरना आप 100 1000 भी ले सकती हैं. अच्छा जी, आगे जाते हैं. कोएफिशिएंट ऑफ वॉल्यूम कंप्रेसिबिलिटी को हम एक्सप्लेन करते हैं. कि कोएफिशिएंट ऑफ वॉल्यूम कंप्रेसिबिलिटी क्या है। देखें, दिस इज अ सॉइल स्पेसिमेन, V0 is the original volume of the soil specimen, and delta V is the change in the volume due to change in the stress. जब आप change of stress करेंगे, there will be expulsion of water, and then there will be a change in volume of the soil specimen. That is because the water has gone out. So what is MV? MV, which is coefficient of volume compressibility, is the change in volume of the soil specimen or at the site, दोनों हो सकते हैं, divided by original volume divided by per unit change in stress, per unit change in stress. इसका मतलब ये है कि अगर आप यूनिट चेंज करें स्ट्रेस में तो डेल्टा वी और वी नॉट क्या होगा? Simply means this: by changing a unit stress change, right, how the volume would change in relation to the original volume. If we keep the area same or unit, delta V would be equal to delta H, and V naught will be equal to H naught. And 1 over sigma prime minus sigma naught prime. So we can write this equation in terms of heights. This. Now we know that, as we proved, delta V over H naught is equal to E naught minus E1 over 1 plus E naught. So we can put this, replace this part by this equation. You see, and ultimately we will get this. E naught minus E1, 1 plus E naught, 1 over sigma prime minus sigma naught prime. So how you will find this? You will find this from this curve, right? This is sigma naught prime, this is E naught prime, this is sigma 1 prime, this is E1 prime, right? So if this, you know these four things, these four parameters, put these four parameters here, you see, you will find the value of MV. You got the idea? The units of MV are inverse of stress. You see, delta V over V naught, the units would cancel, and this 1 over sigma, so the units would be inverse. That would be equal to meter square in per meganewton or per kilonewton, right? They are inverse of stress. One thing important to note that MV is not constant. Rather, it depends upon the stress range. You see, because the curve is non-linear, so if you select 2 points here, 1 point for example here, and 1 point here, you will have different stresses, different values of MV. So they depend on the stress range that you have selected. आप समझ गए? So MV, one person would have 1 MV for a soil, the other would have another value of MV for the same soil, depending upon what stress ranges he has considered. So actually, what stress range you would consider, that depends upon the problem at hand. For example, you got this curve from the laboratory. Sigma naught prime is the stress at the site, ठीक है ना, at certain point, and you find E naught. Now, because of the building, the current stress would increase from sigma naught to delta sigma. So that delta sigma prime is the load that would be caused by sigma naught minus delta Z, that delta sigma is the stress caused by the structure, right? And the corresponding void ratio is U1. So you put these values into the graph and you will find MV. That MV then you can use for the settlement analysis. But the problem is this, at the time of test, you do not know the building pressure. You don't have, the laboratory technician has no idea of what the MV would be, right? Of what the MV would, what the delta sigma would be. What would be the stress caused by the structure? So in such case, British code says that you take delta sigma equal to 100 kPa, which is roughly equal to 1 ton per square foot. 100 kPa. Right, so that's how explain the rate. Take, and it is here somewhere written here in the British standard. Do you have any question?
No, sir.
Okay, so we finish our class here now. Okay? If you have any question, you can ask. We have done a lot of things here. You see, if you want, I can repeat the whole thing for you again as a summary, because still we have time and I don't want to leave earlier. Start working. Sure. Now come to the process again. You see, this is the building. This is imposing some stress on the soil below, and the elements are undergoing compression. Soil layers are going under compression. Our concern is to find this delta C because of the building load. So what we do, we take undisturbed soil specimen, bring it to the laboratory to conduct odometer or one-dimensional consolidation test. The data that you obtain from this test, you process it and find CC, CR, MV, and some other parameter that we are going to discuss in future, in coming lectures. These parameters then you use in the consolidation equation. There are a couple of them, right? And this would give you delta HC. But these equations not only give you delta HC, but also the time when this delta HC would occur. So in effect, we would get a curve like this. This is times an hour, and this is consolidation settlement. As the time passes, the settlement increasing, but at a lower rate. Okay? Rate of settlement would decrease, and at a point it would almost becomes constant, no more increase. That corresponds with the delta CF, which is final consolidation settlement. So the first part of this chapter corresponds to find how to find delta C, and the second part of this chapter would discuss the rate of settlement. So at the end of this chapter, you will learn how to draw such curve. That's important. Consolidation test will give you such kind of graphs. As you increase the stress on the soil specimen, the void ratio would decrease. As you decrease the stress, the void ratio would slightly increase, and then there is a recompression. If you plot this data on the log curve, we have distinct two zones. two type of curves. One is linear and one is curve. The curve we call recompression curve because we are recompressing it, because in the past there was a maximum stress. So we are taking the soil specimen to that stress level. When we are taking the soil specimen to that previous maximum stress, we are actually recompressing the soil specimen and we have a curve part. And once that stress is exceeded, we have a version curve where the maximum stress is exceeded and the current pressure is actually the maximum one. There wasn't any pressure greater than the current pressure acting on the soil specimen. Okay? So this linear curve, we call it version compression. Its slope we called CC, and this part we called recompression curve, right? So this pre-consolidation pressure is the pressure that has acted on the past. This is pre-consolidation pressure. Okay, na? Using Casagrande method. If this pre-consolidation pressure and the current pressure at the site are equal, then we have normally consolidated clay. If the current pressure is less than sigma p prime, we have an over-consolidated clay. These are different construction that is used to correct the laboratory curve. We cannot to the field curve, and this is a correction carrier for over-consolidated clay. The difference is between NCC and OCC that here you will have CR and CC, both slope. Whereas for normally consolidated clay, we only have one line which is CC, compression. How to find the slope of the CC? That is delta y over delta x, which you find from this curve. So this equation you obtain, and this recompression curve index CR, the same equation. The difference is this: the 2 points are selected on the recompression. If you select 2 points on the recompression, any 2 points on the recompression line, and apply this equation, you will get CC. The same equation if you apply, select 2 points, any 2 points on the recompression part. No, sorry, compression part, you will get the slope of the CC. Okay, okay, that's all.
Excuse me, sir.
You can leave. You can leave the class.